The changing speed. Sometimes you don't have the ability to do that because a lot of the effects, more modern effects, would be to play something into a box or a signal chain and have it be changed at that moment or relatively close to that moment. So the way I don't really fully understand this, but the way I try to get my mind around it is to set up an experiment like so. You're playing a guitar and you're plugged into an amplifier that's strapped to the back of the truck. And what I ran into is that really what they're using is the principle we studied, and that's the principle of Doppler effect. So the truck drives away, and as it's driving away, you play the guitar, and what you hear is now a delayed version of your source. And when it arrives at you, it's stretched out a little bit, and it's lower in frequency. But what happens when the truck gets so far away that, well, one, you can't hear it, and number two, the delay is so long that it becomes useless. So you have another truck that's right next to it, and after about 20 seconds of it speeding away, you set that next truck going at the same speed, and then you start to hear this one instead of the one that's too far away, and another truck, and another truck, and another truck. And if you can do that, if you can work that out with circuits or digital, you have what's called a delay line. So, delay line. Yeah. It looks, this is one representation I found of it. It functions in principle of the Doppler effect. The dots, I can't figure this out quite honestly, but you will see that there is a sawtooth wave here where truck number one, right, is too far, it's getting close to being too far delayed. Because we want to be in this kind of 45-degree spot for us to have the sense of it being linear with our input. But truck number two is here, so ignore these. Well, I'll mention these lines here are just amplitude. So you see initially here somebody starts playing the guitar, and there is a delay. You won't get, as we go forward in time, you won't get any sound until here. So there is a delay, but that delay is negligible. And then it's very loud once you start to hear the first truck, so to speak. But as the delay gets worse and worse and worse, we got to switch to truck number two. They shorten the loudness of that first source, and they increase the loudness of the second source. So you read it across. So at this point in time, you would be hearing these two, delay number one and delay number two, but you hear mostly delay number two. So that's the best
kind
side.
of like adding them together, and it sounds like a continuous thing?
Yeah, it makes it more continuous, and you jump forward. You jump forward in time, right?
Yeah.
Because these is very, very much delayed, and this is less delayed.
Right.
So you jump forward. You're keeping up with the input signal by using a delay line, and they use it. Well, so that's just early computer memory was this, I guess.
Really?
I don't know.
Like, I can say, wow.
It's kind of neat, and I mean, you can think you could get pretty good if you had more than just one. You had like multiple ones. Oh, and they also put the delay. Each other line is out of phase, so it helps to somehow. Nice that I mentioned that. So yes, we've been talking about sampling. So that can be used in analog. What we just described, delay lines can be analog, digital, or some sort of circuitry or tape. It could be, it can be used in a bunch of different ways. And of course, they've been using it for a long time. But now we're digital. So what helps me is to remember that speed is not going to really change here anymore. Where we would change speed, we're now going to be able to manipulate the wavelength using samples. So speed usually should stay fixed at one of those rates. They say hertz, and we would think of cycles, but actually that's, like you guys are pretty good on sampling, so that's like sample points, like how often we're taking a record of the number. And it can get quite impressive, 192,000 times each second we're taking a value. So that's going to pretty much stay the same in the digital realm. Frequency is the pitches that we hear, and wavelength is the distance between crest and burst, or sample position. So if we treat sample position as wavelength, here's our wave. Let's call this 10 samples a second. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if we see 1 second represented, we get 10 values, 10 numbers, and we can kind of generate a wave from that. If we want to change this wavelength, we don't change the speed. we're still going to stay 10 samples a second. All the difference is we're going to take that wave, we're going to render it as a wave, and we're going to resample. And instead of using 10 values, we're only going to use 5. And when we do that, it causes a change in the wavelength and also a change in pitch and time. And it would look like that. There's the same wave, only using 5 samples. It's been resampled. And it only plays back at half a second as opposed to the full second. So we have our delay problem again. We sped it up, we have a higher frequency, in this case up an octave. We doubled it, but we're only at half the time. So we just duplicated. And we're back to having, and this is very small, of course, so we're back to having it fill the time that we had when we started. So these waves can be divided into small sections, resampled, and then repeated as necessary to fill whatever length you want. And this sound we're looking at has been shifted. Shifted up. That's supposed to say up. I don't know why I wrote it that way. It's for editing. The sound is back to its original length. What you would call this block here is grain size. You don't want to call it slice, right? Because slice is something with loops, it's something totally different. But it is kind of like a slice. But you call it grain size or sample block because it's so awfully small. Now, if you made this very big, you wouldn't be cutting up the wave very much, and it would sound pretty doggone good. If it were maybe you only cut it up once every, or 3 times every second or something like that, you're going to have a hard time hearing those very small changes between the slices. But your timing could get off by almost a third of a second, which would be noticeable. But if you use a very small grain size, you could get very precise timing, and what would suffer would be the wave. The wave would be out of, it would be jumping around a lot, so your wave is now messed up a little bit. But of course, they have very sophisticated ways and some elegant ways of accounting for that and repairing it. So that pretty much handles resampling, and that's the modern digital way of changing pitch, which can be done awfully fast. So now, detecting pitch, this is, you guys, we saw this in one of the lectures, and this is, I can't explain it, quite frankly, but basically we're taking a wave, in this case a square wave, we're trying to find out what the components were that made up the square wave. How, what were all the contributing factors that added together to create this wave. And if it's a very complex wave, they use a Fourier analysis first, and then a transform to apply that somewhere else. And that's what's being done in a lot of different mathematical fields, but it's of interest to us in sound. So that's the definition I stole from Wikipedia. It decomposes a periodic function. I guess I read a couple places it has to be a periodic function of some kind. Otherwise it wouldn't make any sense, and they couldn't do this analysis. So they're doing these Fourier, but if we look at this here, what are we looking at really? Well, we're looking at a very short instance in time. So it gets more interesting, like we just saw a moment ago when we looked at, here's another representation of a Fourier analysis. Energy, we're looking at energy that's in an instant in time, all the frequencies represented, a fundamental and other partials, or other components of a wave. That's a Fourier analysis, left the R off. But we have to add, this is what's cool, because when we get into computers, we don't have to do it in real time. Now we can analyze these things and do more sophisticated computation. Here we have now included time. That's the major difference here. The bright spots are the louder spots. Down here is low frequency. Down here is high frequency. But we can read it left to right. So this is a male voice saying the words 19th century. And you have low energy here, and you have high energy here. And I tried to say it a bunch of times to see if I could make it out, but I can't. But we can see where there is an energy, and we can see where there is. But that's useful because not only are we limited by just looking at one very small moment in time. Now we can look over the course of a few seconds, and that will tell us a lot more about whether that was a pitch or it was an overtone, how much energy it had, and when it dwindled. And if you put it in 3D, you can see it like that. You can see low frequencies and high frequencies in the way that they dwindled off. So time, frequency, and intensity. So the computers are analyzing this information, and it's doing a pretty good job, but like with Melodyne, it needs some help. So here's kind of where the computer hands it off to you as a user to get creative with this. These are great videos. This is one software manufacturer from Germany that actually doesn't charge you to learn how to use the software. This is really nice. Oh yeah, choose a video. Polyphonic note detection. Yeah, this is now the state of the art. We are taking composite wave and actually separate out what frequencies, what notes.
Welcome to the Melodyne Editor Tour about checking and editing the detection of notes within polyphonic material. Here we have some freshly analyzed piano chords. If you listen closely and compare the music with what you see, you will quickly realize that this note here is not part of the recording. Also, here we definitely hear a note, but the corresponding blob is missing. To correct these misinterpretations, select the Note Assignment tool, which leads to Note Assignment mode. Now you see solid blobs representing active notes and hollow ones representing potential notes. Potential notes are those that during the detection were classed as overtones of some other note rather than notes in their own right. By double-clicking, you can now deactivate superfluous notes and activate potential ones. So let's deactivate this C sharp, which doesn't belong there. In deactivating the higher C sharp, we have caused the lower C sharp to be redrawn more thickly. This is because the spectral energy previously ascribed to the higher note, when it was assumed to be a separate one, has been reassigned to the lower one, of which it is now considered to be an overtone. There are some more overtones mistaken as notes in our example, so let's deactivate them too. With this hollow blob here, it is the other way around. It is mistaken as an overtone. A simple double-click converts it to an active note. The same goes for this one.
So I've got one more of these. I say that's what the magic of Melodyne is actually, is getting this, well, polyphonic in particular. It's knowing and using your ear still, and being musical and being able to remember what it should and shouldn't be. Of course, once you get these, you can move these around and change pitches, and it sounds pretty good. So you can make new chords, or you can put it back into a different key. Let's look at some other. Do I have so little time, or?
Yeah, go ahead.
These are some